My name is Sarah Arvison. I'm working in the Tisdale Lab in the Department of Chemical Engineering. My project is on organometal halide perovskites for application in solar cells. My project is focused on synthesizing a certain kind of perovskite. It's called methylammonium lead bromide. So it's this big methylammonium cation that's in the center of a cage of lead and bromine ions. And currently, I'm going to try to synthesize something that is a hybrid of both lead bromide and lead iodide. So when I'm weighing out my chemicals, it's actually very pertinent that I get the right amount exactly on the scale, because if there is even a slight difference in the molar concentration of the starting precursors, you can end up getting a different compound, and then you might analyze something that you weren't prepared to analyze and think it's something else. Now I'm going to add some DMF into the lead bromide I just measured as a solvent so that the lead bromide can evenly distribute for when I mix it for the compound. A lead bromide doesn't dissolve that easily, so I'm going to go ahead and put a stir bar in and let it stir and heat for a while on the hot plate. So I just put a little stir bar in this vial, and I turned on a magnetic field in the hot plate that's going to allow the stir bar to rotate rapidly and mix it. And I set it to about 60 degrees Celsius so it can heat as well. For the lead bromide to dissolve in the DMF by itself just at room temperature, it would take a very long time to dissolve. However, if I let it heat for a while, the heat acts as a catalyst and it will quickly dissolve up those molecules. So once this dissolves, it's properly heated and stirred, I would weigh out some methylammonium bromide and some lead iodide. I would take appropriate molar concentrations that I calculated earlier and mix them together in a little vial. So I will let the solution of methylammonium lead bromide iodide sit for at least 8 hours, sometimes overnight, to react so that all the reactants can really get in there and mix well. This is one that has been sitting out for about a day, and it's ready to go, ready to be drop cast. So when I drop cast these films, I pipette about 100 microliters or so, enough to cover a glass cover slip. And I have good control when I do it out here, just in air at a bench, because I can drop it drop by drop onto the cover slip. DMF is a solvent that evaporates at a medium sort of pace. So I will probably have to let this sit overnight, and when I come back in the morning, there will be crystallites. So once the solution has been drop casted and let to sit for sufficiently long enough time so that the solvent evaporates, the end product is these little orange crystallites. And you can see that they tend to form towards the edges, which has become a problem, which is why I started to spin coat them. Spin coating actually gives much more uniform coverage, and contrary to my initial belief, a spin-coated film made with exactly the same initial solution has very different optical and structural properties than the drop cast one. This is an SEM image that I took of one of the bulk films that I drop casted at room temperature, just pipetting outside on a cover slip. You can see that there are lots of well-defined cubic and tetragonal crystals. There are little cracks from annealing, and there are pretty big grain boundaries. Now these could act as traps for electrons and holes and excitons in a solar cell. In contrast, this is an SEM image of a spin-coated film. It's made of exactly the same ingredients as the previous one, but it's much thinner. You can see that those beautiful cubes and rectangular prisms start to disappear, and you get a more disordered, non-homogeneous morphology. These organolead halide perovskites were discovered a couple of decades ago, and they were known to be some kind of special something. But just around this January, they became a very hot topic for application in solar cells because they have interesting transport properties like high electron transport of inorganic materials, but it also has the mechanical plasticity of organic materials. Now, this would be very beneficial in solar cell use. They have really high solar cell conversion efficiencies. The first ones were tested at about 9%, and with silicon at 12%, it's approaching the efficiency of silicon very quickly. So we're not really sure whether it's better to have disorder or order in these perovskite structures. As you can see from the SEM images, we can achieve both disorder and order from these structures. So what is required is more testing on the electron transport properties to really see what sort of structures of these perovskites we would want.